Okay, in this presentation we are going to look at we're going to continue on with the binomial distribution. So we're going to look at an example here. So essentially what we've done is sort of seen the binomial distribution and sort of introduced it in the context of number of trials and number of successes. Okay. Now, so let's assume that 5% of all resistors manufactured by a particular company are defective. And we purchase 20 of these resistors, and we're interested in the number of faulty resistors. Okay, in our batch. So essentially what we're going to do here is, it's slightly weird to say that a defective resistor here is a success. I'm not going to use the word success here, but that's how we would usually look at things. Okay, so let x be the number of faulty resistors received. So x is some random variable, and it's a number between 0 and 20. Okay, so we could have 0 faulty resistors, and we could have as many as 20. Okay, so anyway, it's clear that x is a binomial random variable with n equal 20 and p equal 0.05. So this gives us the probability of this key part here is the probability of, for an unspecified number of, for x, where x is 0 to 20, what is the probability of that number of faulty resistors. So this is the formula that we've sort of developed in the last presentation here. Okay, and we're going to use it. So n is equal to 20. So just essentially what we're doing is just like n is equal to 20 and p equals 0.05. And if p equals 0.05, 1 minus p equals 0.95. So essentially just set up this component here, this expression here. Okay, so we simply plug in the values for x into this formula to work out the probability of receiving a certain amount of defective resistors. So let's have a few examples. Probability of no defective resistors, probability of x equal to 0. Well, in this case, 20 choose 0. Remember, 0 factorial is 1, so this works out to be 1. Okay, just remember that. I pointed it out before, I'll point it out again. 0.05 to the power of 0, again, that is going to be 1 also. Anything to the power of 0 is 1. And 0.95 to the power of 20, just a little bit of calculator work. So essentially what we should end up with is 0.3585. Okay, 0.3585. That's the probability of no defective resistors in a batch of 20. Okay. Just remember, actually, just before we get into this, the expected number of defective resistors is 1. Okay, n times p. Okay. So now, at least, so no defective resistors. At least, this is an interesting question that often crops up. Okay, at least one defective resistor. So this is 1, 2, 3, 4, as many as 20 defective resistors. Okay, this is the complement of no resistors. So it's the complement event, none or some. Okay, so to calculate the probability of at least 1, we would just simply 1 minus 0.3585, and we would get 0.6415. So that's the probability of getting at least one defective resistor. Okay, so that's just always remember, handy to remember that. That's the complement rule, and just if you're yeah, just to sort of always keep it in mind. Okay, so I'll just continue on here. Sorry, 3 defective resistors, probability of x equal to 3. From 3, choose 20. That is 1140. 0.05 to the power of 3 and 0.95 to the power of 17. Bit of calculator work. Okay, so if you're not familiar with binomial coefficients or the choose operator, essentially bit of revision on that first. So okay, the probability of 3 defective resistors exactly is 0.0596. Okay, now let's go down here. What is meant by the probability of receiving? What is the probability of receiving more than one? Okay, so what does that mean? Essentially what I'm sort of getting at here is the language here is very important. Okay, so more than one. this is different from at least 1, which is what I had a look at here. Okay, so I'll just highlight this in again. At least 1. Okay, defective resistor, more than 1. Two different questions essentially. So the probability of x greater than 1 can be rewritten as the probability of x greater than or equal to 2. Okay, that's probability 2, probability 3, probability of up, all the way up to 20. Now, so there's 19 calculations that you could carry out there and just add them all up together. Do you want to do that? No, you don't. This is where the complement rule comes in again. Okay, what's the complement event of that? The complement event of probability of x greater than 1 is equal to essentially the complement of this is this. This is, remember, this is probability of x greater than or equal to 2, and that's the complement of probability of x less than or equal to 1. Okay, so essentially what you should do here, and I sort of flagged it already, is that you calculate the probability of x equals 0, or x equal to 0, and the probability of x equal to 1. Okay, we did that one already, 0.3585. So essentially what we have to do here is just carry out the calculation again. From 20, choose 1. 20, 0.05 to the power of 1 is 0.05. So 20 times 0.05 is 1. 0.95 to the power of 19, very close essentially. So it's essentially close numerically. That's the probability of x equal to 0, probability of x equal to 1. Together, the probability 1 or less is 0.7359. The complement of that gives us 0.2641. So the probability of x greater than 1 was 0.2641. Okay. And let's keep going here. Just I'll finish up now on this. What is the probability of receiving between 2 and 4 defective resistors? Okay. Now, this is something actually that like tables comes in quite handy, but there are such things as binomial tables where you can look things up. Okay. For example, Murdoch-Barnes, I think it's table 8 or 9, I'm not quite sure. But anyway, let's just answer the question using the tools I've introduced already. So the probability of between 2 and 4. Now, first off, what I'm more interested in here right now is just how I express that mathematically. 2 less than or equal to x less than or equal to 4. Okay, that's how we sort of express that mathematically. Now, that's essentially 2, 3, or 4. Between 2 and 4 means 2, 3, and 4. So essentially work it out the same way. Calculate each of them. Now it's sort of it's getting a little bit repetitive, so but you can sort of see how we can calculate it there. Now I'm not going to go into that. I'll just give you the answers. You can try it out yourselves. See if you get those answers. 0.1887, 0.0596, and 0.0133. Okay. Add that up to get 0.2616. Okay. So, how many defective resistors would we receive on average? Now, I sort of stated that one already, just to sort of highlight it. But we expect to get one resistor. The expectation of a binomial random variable is n times p. Okay. What is the standard deviation? Well, let's first off look at the variance. N times p times 1 minus p. 20 times 0.05 times 0.05 is 0.95 is 0.95 resistors squared. Now that's why a lot of people don't like variance, because it's often expressed in units that are very unusual. For example, squared resistors are squared units of squared dollars or squared seconds. So what will often happen is that we would sort of state things as in terms of standard deviation, because that's just is given in the same units as the mean or our expectation. Just simply get the square root of the variance. Okay. I think I have one more question here, so I'll just keep going. Oh, this is a sort of homework question. I'll do this in this sort of tutorial section. Okay. So that is it. We'll leave that there. That's a defective resistors example. Okay, and that's a question to set up for another exercise. That's a sort of tutorial question.